Hello everyone. So today we are going to start a course on Laplace transform, and in this lecture we are going to study the definition of Laplace transform. So let f be a function defined from the domain 0 to infinity to real. Then the Laplace transform of function ft is defined by uh, L of ft is equal to 0 to infinity e raised to power minus st ft dt. Okay. So this symbol L of ft means the Laplace transform of function ft, and its value will be equal to the uh, value of the integral if this integral exists, and the integral is improper integral from 0 to infinity e raised to power minus st ft dt. And if we integrate this with respect to t and substitute the limits of t, then we will get a function of s. Okay, so we can also write the Laplace transform of ft. We can also denote it by f of s, because the right hand side integral, if it exists, it will be some function of s. The second thing to note is that the right hand side improper integral is to be solved, and we know that it can be written as limit b tends to infinity integral 0 to b e raised to power minus st ft dt. Okay, so by definition the Laplace transform of any function is this integral value if this integral value exists. Okay, so first question that exists is that does every function have a Laplace transform? Then the answer is no. Every function do not have a Laplace transform. So one of the example may be that the function 1 by t. Okay, so this function do not have Laplace transform. Similarly, function say e raised to power t square, that will also not have a Laplace transform. So the second question that will exist is that what functions will have Laplace transform then? Okay, so to answer that question, I will first review two definitions. Okay, so the first definition that we should know it is the about piecewise continuous functions. So a function f is called piecewise continuous on the interval ab. Okay, if there is a partition of this interval. Okay, so this interval a to b is partitioned with x naught to xn. Okay, such that the function is continuous on each subinterval xk plus 1. So that means k value 0 1 2 so on. So x naught to x1, x1 to x2, x2 to x3 and so on. So in each subinterval, okay, the function is continuous. Then this function will be called piecewise continuous, and the second condition is that the sided limits of each point xk is finite. Okay, so it has this sided limit at each point xk. That means uh, if I consider the subinterval x1 to x2, then in that function is continuous, and the limit x tends to x1 is finite, and limit x tends to x2 is finite. That means the function do not blow up at the endpoints. Okay. So for example, say this function ft is equal to uh, t when t varies from 0 to 2 with open on upper side, or t square minus 1 when t varies from 2 to 5, and 3t plus 1 when t varies from 5 to 8 with not taking value of 5. Then this function is piecewise continuous on interval 0 to 8. The function is defined from 0 to 8. Okay, so it is piecewise continuous because the function ft equal to t is continuous in this interval, t square minus 1 is continuous in this interval, and 3t plus 1 is continuous in this interval. And when t approaches 2, then this is finite. Here when t approaches 5, it is finite. Okay. Say I take one counter example also. Say for example the function is 1 over 3 minus t in this interval and 3t plus 1 in this interval. This function is not piecewise continuous on 0 to 8, okay, because ft is defined from 0 to 8. So because of the first piece, when t approaches 3, okay, from the left, okay, then this 1 over 3 minus t it blows up. Okay, it is not finite. Okay, so this condition is not satisfied, that it has sided limit at each point x. Okay, so this is not a piecewise continuous function. Okay, the second definition is the function of exponential order. So a function f having domain 0 to infinity and up to codomain is r is said to be of exponential order alpha if there exists a constant m positive and alpha such that the magnitude of ft is less than equal to m e raised to power alpha t for sufficiently large t. So that means after some point, when if your t is increasing, so with t the this exponential function is growing much faster than the modulus of ft. Okay, so this can be viewed as that if you have a any function ft and this exponential function e power alpha t, so this exponential function grows faster than this ft. Okay, so then the function ft will be called a function of exponential order. So one example is, say, function ft is equal to t power n, that means a polynomial type function. They are of exponential order since because of this. Okay, t power n can be written as less than equal to n factorial by alpha power n e power alpha t for any positive alpha. So this is like m, and this is true because we know that we can expand exponential into infinite series. So we can write e power alpha t as summation alpha power n by n factorial t power n varies from 0 to infinity. This exponential has a infinite series. So t power n is just one term over there, so it is always less than this. Okay, so polynomial type terms, they are of exponential order. Okay, uh, counter example can be, say, function e power t square. Okay, because it is not of exponential order, because when t increases, this grows much faster than this e power alpha t for any alpha. Okay, so because it is e power t square, okay, so the growth is much faster than this, so it is not of exponential order. So with these two definitions known, we can now take what exactly are the sufficient conditions for the existence of Laplace transform. So if f is a piecewise continuous on 0 to infinity and of exponential order alpha. Okay, so if you have a function which is piecewise continuous and also the function is of exponential order, okay, then the Laplace transform of ft exists for s greater than alpha. Okay, and once this exists, then we can write it as some function of s. Okay, and this immediately results in this, that the limit s tends to infinity fs must be 0. Okay, so this is the additional condition. Okay, we'll prove this result. Okay, that if f is piecewise continuous and of exponential order, then the Laplace transform will exist. Okay, so to prove this, since f is of exponential order, then by definition there exists a m positive and alpha such that this holds. Okay, modulus of ft is less than equal to m e power alpha t when t becomes sufficiently large, that means t is greater than some value t. And then if we calculate the Laplace of ft, okay, Then Laplace of ft is by definition this integral 0 to infinity ft e power minus st dt, and this will exist if this integral exist or this integral converge. Okay, so we divide this integral into two parts, 0 to t and t to infinity. Okay, and we call the first integral as I1 and second integral as I2. Okay, now since the function is piecewise continuous, so the I1 integral, which is from 0 to t ft e raised to minus st dt, it is it exists. Okay, because it has a finite limit. Okay, and it is piecewise continuous, so this integral exists. And for the second integral, the improper integral t to infinity ft raised to minus st dt, for this integral we note that for every t greater than t, uh, this holds e raised to power minus st ft modulus, because of modulus of ft less than this is less than m e raised to power minus s minus alpha t. Okay, so we just substitute it here. Okay, modulus of this is less than equal to modulus of first into second, and then we can substitute it, and then exponentials are combined to write this. Okay, and so if we calculate the integral value of this second, then t to infinity modulus of ft e raised to minus st dt, this modulus is substituted, so it is less than equal to m t to infinity e raised to minus s minus alpha t dt, and this integral is less than equal to this integral where limit is 0 to infinity. Okay, because t is positive, and this integral we can solve. Integration of exponential is exponential divided by minus s minus alpha, and then we can substitute the upper limit minus lower limit, and at upper limit the value of exponential will be 0 only if this term s minus alpha is positive, that means s is greater than alpha. So when s is greater than alpha, the upper limit will lead to 0, and the lower limit value when substituted will give this result, m over s minus alpha. Okay, so the second integral I2 also exists when s is greater than alpha. Okay, so I2 converges for s greater than alpha, and I1 is already converging, so the sum, which is Laplace of ft, exists for s greater than alpha. Okay, so that's the proof that the Laplace transform of function will exist if function is piecewise continuous and of exponential order. So this is only a sufficient condition for the existence of Laplace transform. Okay, uh, when we say sufficient, that means whenever the function is piecewise continuous and exponential, the Laplace will exist, but this condition is not necessary. Okay, that means there exist functions which do not satisfy these conditions, but their Laplace transform still exist. Okay, so I'm just giving you one example. Okay, the condition was not necessary. Okay, so for that, consider this function ft is equal to 1 by root t with t positive. So this function, when t tends to 0, okay, this blows up, that means the function is not piecewise continuous. Okay, okay, it is not a piecewise continuous. However, the Laplace transform of this function exists. Okay, so we'll just prove this result, that the Laplace transform of any function by definition is this integral 0 to infinity ft e power minus st dt, and here ft is 1 by root t. Okay, so to solve this integral, we substitute st as u. Okay, so we substitute st as u. So dt will be du by s. Okay, so st as u, dt will be du by s, and here t is u by s. So if you substitute this, okay, so 1 by root s, 1 by root u e raised to power minus u du, and limit when t goes to 0, then u goes to 0, when t goes to infinity, u goes to infinity, so limits are same. And this integral is well known, it's a gamma function of half. Okay, so it has a value, and the gamma function of half, we know it is root pi. So this uh, Laplace transform of this function 1 by root t is root of pi by s. Okay, with s positive. So that means that we the sufficient conditions that whenever function has exponential order and function is piecewise continuous, the Laplace will exist, but these conditions are not necessary. Even if the conditions are not satisfied, the Laplace transform may exist. Okay, and one more thing I said is that if Laplace transform exists, then limit s tends to infinity fs must be 0. Okay, so that immediately says that any function fs without this behavior, okay, that limit s tends to infinity fs equal to 0, if it is not satisfied for any function fs, then that function cannot be Laplace transform of uh, any function ft, okay, or some function ft. So for example, if I have s over s plus 1 or sine of s square over s minus 1, s square over 1 plus s square, you see that in these function, if I take limit s tends to infinity, their limit is non-zero. Okay, so they cannot be Laplace transform of any function ft. Okay, right. So with this basic, I come to this point that now we can define the Laplace transform of some elementary functions, and it is important to remember the Laplace transform of these functions which I am going to present, because once you remember these results, there are seven elementary function whose Laplace transform I want you people to remember. If you remember the Laplace transform of these seven functions, then you can solve the Laplace transform of any complex function. Okay, any function in general. So I'm going to give you seven functions FTs and their Laplace transform. Okay, so you need to remember the function and its Laplace transform, and also I'm giving the proof that the function FT has this Laplace transform. Okay, so the first function is constant. Okay, that means if FT is 1, okay, its Laplace transform is 1 by s. Okay, with s positive. And the proof is very simple. The Laplace transform of ft, we know it is the integration e raised to power minus st ft dt. Okay, so if ft is 1, then Laplace transform of 1 is integral 0 to infinity e raised to power minus st ft dt with ft value 1. Okay, so simply 0 to infinity e power minus st dt, and the integral of exponential is exponential divided by the derivative of minus st, which is minus s, and limit 0 to infinity. So at upper in, when limit infinity is substituted for t, this value will be 0 only if s is positive. Okay, so and at lower limit this will be 1 by s. Okay, so its value is 1 by s only if s is positive. So this condition is all is due to this upper limit when t goes to infinity. Okay, so I just want to make a point here that although their conditions are there, but you need not remember these conditions for now. You just need to remember that if function ft is 1, its Laplace transform is 1 by s. Okay, and proof is very simple. So second function is the exponential function e power at, where a is some constant. Okay, so its Laplace transform is 1 over s minus a. Okay, and condition is s greater than a. Okay, which you want, then you can remember. Otherwise you just remember that the Laplace transform of e power at is 1 over s minus a. Condition is automatically generated when we do the proof. So Laplace of e power at, by definition Laplace of any function is integral 0 to infinity that function into e power minus st. So function is exponential and e power minus st is also exponential, so they combine and we can write e raised to a minus of s minus at. Okay, again the integral of exponential is exponential divided by the derivative of exponent, so that's minus of s minus a. Upper limit this exponential will become 0 only if this s minus a is positive. That means s is greater than a. Okay, so this condition is generated there, and at lower limit exponential becomes 1, so value will be 1 over s minus a. Okay, so this value 1 over s minus a. Okay, and this minus sign cancels out with the minus sign for the lower limit. Okay, So the Laplace transform of e power at is 1 over s minus a. Can you remember this result? Third result is for the polynomial t power n. So Laplace transform of t power n, where n is any real number, is gamma function of n plus 1 over s n plus 1. And if n is a positive integer, then we know the property that gamma function of n plus 1 is n factorial. Okay, so if n is positive integer, then t power n Laplace transform will be n factorial over sn plus 1. Okay, so in general I'm writing t power n, its Laplace transform is gamma function of n plus 1 over s power n plus 1. Okay, the proof again, the Laplace transform of t power n, by definition it is integral 0 to infinity t power n e power minus st dt. Okay, so ft e is to power minus st dt. Now to solve this, we substitute this st as a new variable u, so this becomes e power minus u, and st is u, so dt will be du by s, so this will be du by s, that goes one s outside, and st is u, so t will be u by s, so t power n will become u by s power n, so s power n comes out, so s power n plus 1 s power n from here and 1 s from here. And again this integral is well known gamma function, so it is gamma of n plus 1 over s n plus 1. Okay, so again we have this proof for the Laplace transform of t power n as gamma function of n plus 1 over s n plus 1. The fourth result or the for the Laplace transform is for the trigonometric function sine of at. So sine of at, where a is any constant, the Laplace transform is a over s square plus a square. Okay, so Laplace transform of sine at is a over s square plus a square, and the proof says that Laplace transform of sine at, and again by definition it is integral 0 to infinity e raised to power minus st ft is sine at. Okay, and this you can solve integrating by parts. Okay, I have written the direct result, so you can integrate by part 2 time and then rearrange and combine, so you can write this result, and then you can substitute upper limit minus lower limit. So when we substitute t as infinity upper limit, then this whole quantity will become 0 when this exponential becomes 0, which will be possible if s is positive. Okay, so that's why this condition. So at upper infinity, if s is positive, this whole term will become 0, and for lower limit 0, sine 0 is 0 and cos 0 is 1, so it will give minus for lower limit and minus a, so it will give plus a over s square plus a square, and e raised to power 0 will be 1, so it will be a over s square plus a square, this result. Okay, so again it's very simple. Laplace of sine at is a over s square plus a square. Okay, very simple proof by definition. Okay, the fifth result is for the cosine function. So cos of at, Laplace transform of that is s over s square plus a square. Okay, so Laplace transform of cos at is s over s square plus a square. So again we for the proof we write that Laplace transform of cos at is integral 0 to infinity e raised to power minus st cos at dt. Okay, and again as I said, integrate by parts 2 times. Okay, rearrange the terms and we can write this. Okay, and for the upper limit, if s is positive, this whole quantity goes to 0, and for the lower limit, sine 0 is 0, cos 0 is 1, so it will give now s value from here, so s over s square plus a square. Okay, and e raised to power 0 is 1. Okay, so Laplace transform of cos at is s over s square plus a square. The sixth and seventh are the hyperbolic functions. So sine hyperbolic at, the Laplace transform of sine hyperbolic at is a over s square minus a square, and by definition if we prove this, then Laplace transform of sine hyperbolic at is integral 0 to infinity e raised to power minus st sine hyperbolic at dt, and sine hyperbolic at can be written in terms of exponential functions as e power at minus e power minus at by 2, so exponentials can be combined, so e raised to power minus of s minus a time t, so this type of function, so its integral is 1 over s minus a. Okay, and similarly when the second is combined it will be minus times s plus at. So again this type of function with plus sign here, so its integral value is 1 over s plus a. Okay, and then we can combine these to write that it is a over s square minus a square. So you can remember this result also. And finally the seventh you have to remember is the Laplace transform of cos hyperbolic at. Okay, which is s over s square minus a square. Okay, so similar proof. Okay, Laplace of cos hyperbolic at is integral 0 to infinity e raised to power minus st cos hyperbolic at, and cos hyperbolic function can be written in terms of exponential. Again combine the exponential similar to this integrate, and then combine the s these two terms to write that it is s over s square minus a square. So these seven uh, Laplace transforms of these seven elementary functions. These you need to remember if you want to do the Laplace transform of any function. Okay, so I close this first lecture here. Okay, when these Laplace transform of seven functions, if you remember, and if you combine this with the properties that we are going to study in the next lecture, then combinedly they can solve the Laplace transform for many functions. Okay, so I will see you in the next lecture with these properties of Laplace transform. Okay, have a good day.